This is the first video on section 6.1, tangent planes and linear approximations and differentials. And this is part 1. And so we're going to start with theorem 156, which says if f from R2 into R is a nice function. And what do we mean by nice? We mean that it has continuous partial derivatives. So the partial derivatives both exist and they're continuous. And so we have an equation for the tangent plane at the point a, b, f of ab. And that equation is given here. Z minus the z coordinate, so z minus f of ab, is the partial derivative with respect to x evaluated at ab times x minus a, plus the partial derivative with respect to y evaluated at ab times y minus b. Now this is similar to something that you already know. Recall from Calc 1, we have tangent lines. And so the equation of the tangent line was y minus the y coordinate is equal to the slope times x minus the x coordinate. The y coordinate is f of c, and the slope is f prime of c. So this was the equation of the tangent line at the point c, f of c. Here, we have something similar, but we have an equation, we have a function of two variables, which means this graph is three-dimensional. So the third variable z is a function of the first two. So we have f from R2 into R. So the function value, f of xy, we call that z, and it is defined by a point in the xy plane. And so because we have two variables, we have the partial derivative with respect to x times x minus the x coordinate plus the partial derivative with respect to y times y minus the y coordinate. So let's look at a couple of examples. The first one will be in this video, and the second example will be in the next video. The function we're given, we have z is f of xy is 2x squared y plus y cubed. We're evaluating, we're going to find the equation of the tangent plane at the point 1, 2, 12. In the notes, I did not write the function f of xy. I just wrote z is equal to this, but I'm going to write f of xy here because, okay, I just wanted to write the partial derivatives in terms of function notation. That's the reason I did that. And so we have the partial derivative of f with respect to x is simply 4xy. And then the partial derivative of f with respect to y is 2x squared plus 3y squared. We evaluate the partial derivative with respect to x at the point 1, 2 because we were given the point 1, 2 in the problem. We're going to calculate the partial derivative with respect to y at the point 1, 2 because we're given the point 1, 2 in the problem. We were also given the function value of 12 up here. Sometimes we're not. Sometimes we have to find the 12 on our own. So in other words, f of 1, 2 is equal to 12. And sometimes we have to do that calculation ourselves. So now that we have all of the numbers that we need, we have z minus the z coordinate is equal to the partial derivative with respect to x evaluated at 1, 2 times x minus the x coordinate. And then we have the partial derivative with respect to y at the point 1, 2 multiplied by y minus the y coordinate. And so this process is actually very similar to what you did in Calculus 1. It's just that we have more variables to work with.